Okay, good morning everyone. My name is Tamir and today we're going to be talking about implementing C++ semantics in Python. Now, before we begin, you probably saw this picture on the website. This was my pre-COVID hairstyle, which was a lot shorter. Now it's gotten a bit longer, but it's still me, I'm the same person. Now, before we start, I have a few questions for you. Who here uses C++? By raise of hand. Okay, and as a primary language? Okay, and who uses Python? And as a primary language? Okay. Now, if you have any questions for me, there will be pauses during the talk for that, and there are slide numbers on every slide, so you can always refer to those. So the first question we have to ask is, why on earth would I want to take C++ semantics and get them in Python? I mean, C++ is low level, it's mostly expert oriented, and it's slowly becoming more and more Pythonic as new features make it in. Python, on the other hand, is nice. It's high level, it's beginner friendly, and it has a lot less foot guns. I mean, it hardly happens that you write code in Python and go like, oh, I did not expect it to do that at all. And if you've been to the quiz yesterday, I mean, that's not exactly a fun experience. Why would I want to take that and bring that into Python? Well, at least for me, the answer is resource management. In C++, all resources are treated equally. There's no special handling by the system, you just have to handle everything yourself. In Python, on the other hand, you have garbage collection, so if you allocate any memory, it gets freed automatically, which is very nice, but any other type of resource, be it a file, socket, a DB connection, whatever you do, you need to handle it manually. So it's not like in C, where you actually have to write every call to close the resource. Just a sec. Python does give us some facilities to do that, namely context managers. Context managers are fairly straightforward. Whenever we use them, we use the with statement. And then when we enter the with, it creates an indented block. When we enter the block, the enter method for the context manager is called. And when we leave the block, be it by a return statement, just by getting to the end of the block, or by throwing an exception, we call the exit method for the context manager. If we want to implement our own context manager, we just need to implement the enter and exit methods, and we have our own context manager, and we can do anything we want in those methods. So let's talk about some real code. And this has been redacted from some code I have running in production. You know, it's not the best code in the world, but you have some code in production, you have to live with that. You pay for your mistakes. Anyway, the code is fairly simple. We have a zip file containing hundreds of files. And you want to be able to read them whenever we need to. So initially the object is fairly simple. We open the zip file with the context manager in order to be sure to close it when we're done. We read all the files from the zip file, we unzip them and store them in a dictionary. Then we want to read the actual contents, just call the read method and access the data in the dictionary. Sorry. Okay. Usage is fairly simple. We create a new archive reader, and then we call read, get the value, print it, and everything works as expected. Now, as time goes by, things change. In my case, the archives got larger. From hundreds of files in the zip, it grew to thousands and tens of thousands and hundreds of thousands of files. And that meant the file was a lot larger, and we could no longer just open everything and hold it in memory. It was way too big to be stored in memory. Additionally, the time that took to open the actual zip file just to parse the metadata grew too long to open the zip file whenever we want to read one single file. So we had to do something. We had to open a zip file, store it as a member variable in our class, and only then read the files when we want to. This created a bit of a change in our archive reader. Now in the constructor, all we have to do is open the zip file. We don't need to read from the zip file yet. In the read method, we take the zip file, we open a specific file within it, we unzip that file and return the data. No need for the dictionary. But to get that, we also have to make our own archive reader a context manager so that we can open the file and close the file whenever we need to do that. And this means that we need to add an enter method and an exit method. All fine so far. However, this changes the usage of our class. Like we saw before with the zip file, you use a context manager and use the with statement. Now we need to do that with our archive reader. So if anyone's used that archive reader, we need to change that code. if the archive reader was used as a member variable anywhere, we need to change that code as well, and that keeps propagating higher and higher and higher up the call stack and can pollute a lot of code. Additionally, if we cannot change any part of that code, we would not be able to make the change and use the new archive manager. Well, C++ has a solution for us, namely Destructors. In C++, Destructors is a solution to the resource management problem. And they have three main properties that we are interested in. First, they're automatic, then they're composable, and they're implicit. Let's go over that. First, automatic. Whenever we have a destructor and we reach the end of a block, the destructor is called for the object that goes out of scope. Doesn't matter if it's because we reached the end of the block, whether we threw an exception, or we just returned. The destructor would be called just like with the context managers. Then we have seamless composition. If we have a class and it has no members, everything is okay, our destructor would get called. Then if we add a new member to that class, and when the class gets destroyed, that member variable destructor would be called as well. That just happens seamlessly, we don't need to do anything to make that happen. And additionally, it's completely implicit. Here we have an example, one object has a destructor, the other one does not have a user-defined destructor, and the code is exactly the same. We don't need to do anything special to use that. So if we just add a new destructor to an object, we don't need to propagate a change higher up the call stack, we don't need to change anything, it just works, which is wonderful. So our goal is basically to take this code, which is our current archive reader, which is 11 lines of code, 4 of them are strictly resource management, so boilerplate, and we'll create this code, which is 7 lines and no resource management at all. Everything is automatic, implicit, and composable. Additionally, we change the usage from this weird with statement usage to just, a regular variable usage, which is a lot nicer, and again, does not propagate a change higher up the stack. We just add a destructor, and we're happy to go. Before I continue, just a word of warning. We're going to do a lot of dirty hacks here. Please do not try that at work. If someone saw that in a code review, they would be appalled and probably call you to a conversation and say, hey, what are you doing here? That's not okay. But we're not doing work here. This is for fun. So on our journey towards Python that's more like C++, we have our greeter class to join us. And it's a very simple class just to help us visualize the constructor and destructor calls. When we construct the class, it says hello, and when we call the destructor, it says goodbye. It's a context manager, just like we did before. And when we run it, we simply get hello, and then we have a greeter printed here, and we say goodbye. Fairly simple. Now, let's make sure that everything is automatic. As I mentioned before, context managers are already automatic. They are explicit, but everything happens automatically. If we use the with statement, we are sure that when we leave the scope, when we leave the block, the destructor would be called. Now, things get a bit messy if we want to add another greeter and another greeter, because we keep adding nesting and more nesting, and it's quite common for us to have more than one object in our function. Like 10 objects is not that rare. And as we keep adding, that can get a bit messy. So what do? And instead of stacking everything with nesting, we can move to a proper stack. So we create a new object called the destructor scope. The destructor scope basically holds a stack with the destructors for all the objects that we create. And it's fairly straightforward. We use a list as our stack because it has pop and append. It can use it as a stack, and like vector is the default container for everything in C++. In Python, we use list. And we have an enter method which just returns the same object. That's very common with context managers. We usually don't need to do anything in the enter method. And we have an exit method that goes over the stack in reverse order and destructs all the objects. So we actually call the destructors in the right order. And we have a push method to add to the stack. When our code changes to this, we create a scope. And then whenever we create a greeter, we push that into the scope. And when we leave, everything gets called in the right order. Now, this is nice, but it's very explicit. I mean, I don't want to write all that code for every single object I add for every single function in my code. So next step is to try to make things more implicit. Any questions so far? Okay. Basically, we want to remove, or if we cannot remove, hide all the boilerplate in our code. We want to change from the fact that we explicitly create a destructor scope, we give it a name, create a greeter, we push them explicitly onto the stack, and then it gets destructed to just the simpler code inside. We create a greeter, and that's it, it just works. So whenever we want to hide something, we usually add another layer of indirection. In our case, this is what we're gonna do. First things first, if we don't want to push the greeter explicitly, and you don't want to forget to push the greeter, then we just make sure that when we initialize the greeter, it needs to get the destructor scope. If it does not get that, we cannot create the object. So move the pushing into the constructor and change the code a bit. So now it's a bit more, it's a bit less code, but we still need to name the destructor scope. And I don't really like that. I want to hide that name. So let's say we have the scope. We want to hide it. We want some other variable function or class to have access to it. Well, I guess the best solution is a global variable, though they're always fun. But since functions are being called on a stack and we keep adding new scopes, we'll have to make that global variable a stack as well. So we'll have a stack of destructor scopes like we created before, and wherever we enter a new function, we just push that onto the stack. So we change our destructor scope a bit to make sure that when we create a new scope, we push it onto the global stack, and when we destroy the scope, we pop it off the stack. Very straightforward. We add a new global function to push something onto that stack, and then we can use it in the greeter. So instead of getting the destructor stack explicitly, we just use the global stack, and we're good to go. Now we don't pass any more variables into the stack. Our main basically looks like this. We create a new scope because we have to do that. We create the greeter, they get pushed automatically onto the stack, and when we leave main, they get destructed automatically. But we can do better, we can do a lot better. First, that destructor scope. I don't want to create it in every function I call. That's quite annoying. So first thing you can do, since it doesn't have any code that's related to the actual main function, it only uses global variables, let's move it outside of the main function. This works exactly the same, and now we just need to do it around every call and not inside every function. That's still not the best, so let's create a new way to call functions. We create a call function that takes a function and its arguments. The star args, star kw args is Python's way of doing perfect forwarding. So we take a function, we take the arguments, and then we perfectly forward the arguments into the function after creating a destructor scope. So here we call main, and it works just like before, but it's a bit simpler. But still, I don't really like calling call whenever I want to call a function. Like I wouldn't use invoke every time I call a function in C++. So we go another step of indirection. We create the CPP function that takes a regular Python function and returns a C++ function. So inside it we have a closure. We take the function that we passed, we capture it in the closure, we add the destructor scope and return the closure. Then we have a new function called scoped main, which does the same thing as main, but it's wrapped in the destructor scope. And then, since Python is a dynamic language after all, and we can rebind names to whatever we want, we can rebind the name main to the new scoped version of the function. And now if we call main, it creates the scope and calls the original main we defined. And this is a fairly common operation in Python, taking one function, wrapping it in something else, and assigning it to the original name. So Python added a new specific syntax for that, called the decorator syntax. Basically, instead of calling the function directly, we just use at and the name of the function above a function definition, and it does the exact same work. Takes the function, passes it into the function, takes the return value, and assigns it to that name. So now we can write the main function this way, and it works just like we did initially. It creates a destructor scope, makes sure that everything gets pushed, and returns the value properly. I think this is already a lot better than where we started. It's declarative, which is nice. It doesn't have just weird context managers lying around. It's fairly clean. The contents of the main function look like a perfectly regular function, but it's still explicit. And again, I have to write it every single time for every single function. And we probably want to avoid it. I mean, if I forget doing that, and you just write the main function without it, we would not have the destructor scope, And as we write more and more functions, that could become annoying, especially since if you forget it for one function, you just bind to the function above and things would act really weird. Any questions so far? Okay, now we're gonna start with import hacking. This is where things get really messy and fun. So basically what happens in a file if we want to use our new library with the CPP function in our own code. First thing we do is from CPP, which is how we'll call our C++ library that we use, and we import the CPP function decorator. Then we import the greeter, then we create the main function and use the CPP function decorator. Fairly straightforward. Now, what if I want to do something else? What if I just want to import magic from C++ and have everything else just happen? Well, let's start small. Let's say that instead of only importing magic, I also call the magic function. And I want at that point to do whatever is necessary in the file to get the same results as we've gotten before. So what does the magic function actually have to do? It needs to do two things. One is find out which is the calling module, where was the function called. And two, it needs to modify that module and decorate all the functions within it. Let's see how to do that. In the magic function, we use the inspect module to get the call stack. Then from the call stack, we get whichever module called us. Once we have that, we can return the module. It's very nice that we have that functionality in Python. I wish someday we'll have call stack inspection in C++, but that's probably a long way off. Then we need to decorate all the module's functions. So basically, we go over the module and iterate over all the module's members. The first thing we check is what we're looking at a function. If it's not a function, we don't need to do anything. Then we make sure the function was defined in that module. After all, if we imported like something from the standard library, we don't need to decorate it. We don't want to change the functionality of the standard library. That would cause very weird behavior. And then we set that attribute back into the module. We just use setAttr, which allows us to take an object, a name, and the new value for that attribute. And we call CPP function on the function to decorate it like we did before. And with that, we can write the code as follows. And we just import magic, define all of our code, call magic to make the magic happen, and then call main. Everything just works. But it's quite annoying that you have to explicitly use magic. Magic should be magical and visible and fun. So what do we need to do to actually... Okay, this was confusing. I have a duplicate slide. Sorry. So what do we actually need to do to make the magic call disappear? Well, for that, we need to talk about the actual import mechanism in Python. This is a basic diagram of what happens. When we write from CPP import magic, this is the import expression and we want the import statement, and we want to import magic from the C++ module. The first thing we do is check whether the C++ module is in the global module cache. If it is in the cache, we just move ahead. If it's not, we need to go through 3 steps. First, we need to create a new module object. Then we need to add that module to the cache. And then we need to execute that module. And generally, Python adds the module to the cache to prevent cyclic imports from just re-importing it again and again and again, which is quite unpleasant. Once we've executed the module, we check whether magic is in the module. If it is in the module, we just bind the magic to the name magic in the importing module. If it is not there, we call the getAttr attribute, the getAttr method of that module if that exists, and pass the name that we're looking for, which is magic. Since magic was a function call, we probably want to use a function call as well. So that's what we're going to go for. We change the name of the function magic to _magic to make sure that we don't accidentally just import it directly. And then we create a getAttr method. In there, we check whether the name is magic or not. If it's not magic, no magic happens. If it is magic, we call the magic function. And now everything should work. We import it, the magic function is called, everything gets decorated, and we're done. Except there's a bit of an issue. If you see in the output here, we got hello 1, hello 2, but no goodbyes. Well, if you look at where we're calling the magic function, we call it at the first line of the module. This is before we define the main function. So when we import the module, we check for the calling module, we get our main module, and then we check for members in that module, it's empty. So we decorate all the nothing, and nothing happens. So we need to do something else. One thing we can do is move the import down the line. If we do it the same place we called magic before, it works, but I don't know about you, that does not look magical to me. That's iffy. So we need to do something else. Well, Python allows us to do parallel imports, which means we can just, instead of using the import statement, we can write our own code to import new code. Again, we write the function, it goes by the same way. We pass in the name of the module we want to import, pass the path to that file, so that it would find it, and then we create a module object, we add it to the cache, and we execute it. Fairly straightforward. And now we're going to do something a bit more fun. We get the calling module. Then we take the name of the path and the path of that module and import it again. Since we're executing the module while we import it, we will get the module after it's fully executed, which means all the methods in it have been defined. Now we can decorate everything, and we should be okay. So the magic happens, and we have a recursion error, because we imported the module, and then the module imported magic again, so we imported the module again, so the module imported us again, kept going until Python filled up the stack. Python, unlike some languages, does allow for cyclic imports. It's sometimes useful, you just need to make sure that they stop at some point. Otherwise you get a recursion error. So we need to do something about that. In C or C++, we would use either pragma once or include guards. Here, I guess we'll use an include guard as well. When we import the module, using our parallel import function, we can add a flag into that module. Then, when we execute the magic, we check, is the flag does the flag exist or not? If the flag exists, we don't need to do any magic because we're doing it externally, and we can just continue. And this prevents the recursion error. So now everything should work, right? Well, no. What happens now is we import the magic, we create a new module, we decorate everything, great, but during the import, we execute the module. When we execute the module, the main function is not yet decorated, which means that when the greeters try to push themselves onto the global stack, there's nothing there and we crash. So we need to change the way we call the main function. This is fun because it allows us to do something a bit more like C++. In Python, whenever you double-click a Python file or execute it through the command line, the name of that module is going to be __main___. This means we can check for that to find whether the module that's currently importing magic is the main module or a different module. If it is the main module, we would just check whether there's a main function inside that module, and if there is, we would execute that function. Once we finish executing it, we just exit. So essentially, we check for the main function. If it exists, we run it, just like C++. And this means that you can also remove the main call from our function. We just create the main function, and everything works. Any questions? Okay. So let's look at the greeter again. So far we've treated it as one class, but we're gonna write a lot of classes, not just the greeter class. So if we have here like 6 lines of boilerplate, we might want to be able to remove them. We create the init, which currently just pushes us onto the stack, which is quite pointless. We have the enter function, which does basically nothing, and we have the exit, which is the destructor. You want to reduce some of that boilerplate. Now, since this is a class and we're an object-oriented language, well, the obvious thing to do is just create a base class to do the work for us. So if we have a base class that does something, we can create a constructor here named as the same as the function that operates like a regular constructor, and we have a destructor. Sorry, Python does not allow me to use a tilde in a variable name, so we have underscore instead. Still, in my opinion, better than underscore exit. And we have the destructor, and that's basically the entire greeter class. And we removed all the boilerplate. As for the CPP class, we have a constructor, a destructor, and the useless enter method. In the constructor, we push ourselves onto the destructor scope, and then we check is there a constructor for that class. If there is one, we call it. Then in the destructor, we check either a defined destructor. If we have a destructor, we call the destructor. And that works. Additionally, we might have methods in our class, and we want them to be decorated the same way as we did with the main function, which means that just like we went over the module object and over all the members to look for functions and decorate them, we do the same with the class itself. We go over all the members of the class, check they do not begin with a double underscore because that's special methods and we don't want to handle those. We don't want to decorate the underscore or exit, init, or enter. Then we make sure that that thing is indeed a function and not a variable, and then we decorate it, just like we did before. Let's see where we're standing now. We have a greeter class. It inherits from CPP class, and basically works, but that CPP class is still a bit explicit. I mean, you have to write it all the time, and I want it to look just like Python code, to be completely implicit. I mean, in C++, when you have a class, we don't need to say, oh, and act like a regular class. We just write class, and it works. So what actually happens when we use inheritance here? One very simplistic way of looking at it, which is good for our case, is basically we take all the methods from the base class and copy them over into the subclass. Now, if we're just copying methods around, and we're using Python, which is a dynamic language that allows us to change objects at runtime, we can just assign the methods directly instead of using subclassing. So instead of having a CPP class, we can have a CPP class function that takes a class and converts it into a CPP class, just like we created before. We define all the init, enter, and exit methods. We decorate all the current object methods, and then we just assign the new init, exit, and enter methods to our class and return the new class. This works. Then classes can be used with the decorator syntax as well. So we just use the CPP class function as a decorator and convert our greeter to a CPP class. Now, one last step we have to do here. Since before, we could just check, oh, this is an object. Is it a CPP class? Well, we can check for using isInstance that checks for inheritance in Python. And you can see that the object was indeed an instance of a CPP class. Now that we're not using subclassing, we cannot do that, so we add a small flag in the object that says, yes, this is a CPP class, not a regular Python object. With that, we can go back to the magic function we wrote before and add a similar method function to decorate all the module classes. So again, we go over all the members of the module. We check whether they are classes. Unlike the function we did before, we make sure they were defined in the same module, and then we decorate them just like we did with the functions. So now our greeter looks like this. No hint of context management or resource management anywhere. Our main is fairly straightforward, and everything just works. Any questions? Okay. So let's go over what we did so far. First, everything is automatic. Destruction is automatic. Whenever we leave a scope, we destroy everything that needs to be destructed in that scope. And second, it's implicit. We just import magic from C++, and everything else just happens. We don't need to write any special code, don't need to do anything specific to make context management, resource management work. And additionally, the main function is just called, which is a lot more fun. Our next stop is composition. So let's look back to where we started. We had 11 lines of code, 4 of them were resource management. Now we have 9 lines of code and 2 of them are resource management. I think that's already better. But we have an issue. The destructor is currently called twice. We create the zip file, assign it to a local variable, to a member variable, and leave the constructor. As soon as we do that, the zip file gets destructed because we left the scope. Then when eventually we go to the destructor of the archive, it's called again and we actually destroy it twice. It would probably be okay because it's Python and we don't have any dangling pointers or anything like that, but we're still using already destructed object, which would probably be closed and nothing would work. So we need to fix that. Simple way to fix that would be just to remove it from the current scope. Create a variable assigned to a local member, then remove it from the destructor scope, and we know it would not get destructed automatically when we leave the function. Now, how do we do that? We add a remove function, remove method to our destructor scope. We call stack, which is a list.remove, and pass in the member. We have one issue here. List.remove is equality-based and not identity-based. So if you have two different context managers which equate true, we may destroy the wrong one, we remove the wrong one, which is not a very pleasant thing to do. So we need to take something from the C++ playbook and create a customization object. Here we create an identity comparator. It basically takes an object and overrides the EQ method, which is what Python uses for equality checks. And we use the is statement, is check here, which is identity. It checks identity and not equality. Then we can pass that to our remove function. And then instead of checking for equality, it will automatically check for identity with all the objects. And things will just work as we want them to do. Now we can call remove, and we're good to go. But this is still explicit, and we are working on making everything implicit and transparent. So if you have to do something every time we assign to a variable or get the value from a variable, the obvious thing to do is to use getters and setters. So in get zip file, we just return the value from the right attribute. That's pretty straightforward because we don't need to do anything. When we set the zip file, however, there are several steps. First, if there is already a value in that member variable, we need to destruct that value because otherwise we'd have a dangling object. And then, once we do that, we can assign our new member and remove it from the destructor scope. Again, like we had before with descriptors, with decorators, Python has a special syntax for getters and setters called descriptors. The descriptor has to be a class member variable, not an instance variable. It has to implement the get and set methods, and it may also implement the set name method, which is used to let the variable know which variable name it's assigned to. So specifically here, when we initialize CPP member, when the class itself gets created, not an instance, but the class type, set name would be called for the CPP member instance assigned to the zip file variable with the name zip file, so that it knows, oh, I'm the zip file variable and not a different variable. To create the CPP member class, we implement those three methods. We have set name, which takes the name given to it and stores a private name. Since this is a class member variable and not an instance member variable, we have one for the class. If we have multiple instances, it would still be the same CPP member instance. So in order to actually store values in the class, in the instance, we give it a new name and assign directly to the instance with that name. Then in get, we access the instance with the name we created with the underscore prefix. And when we get the value, and when we set the value, we do just what we did before, but again, using getUtter and setUtter with the private name we created. Any questions? Okay. And then everything just works. We assign to the variable, it gets removed from the scope, it does not get automatically destructed. But we still call the destructor of the zip file explicitly in our destructor, and in C++ we don't need to do that, so we probably shouldn't have to do it in Python either. So we add something else to the exit method we defined before. We go through all the members of the class. We check whether they start with underscore. If they do, they're the private members. We don't want to touch those because then we destruct them twice. We check whether the value currently stored in the member variable is a CPP class. If it is not, it does not have a destructor, we will have nothing to call. And if it is, we call the exit method, we call the destructor, and carry on. So essentially, we just automatically call all the destructors of all the members once we finished calling our destructor. And now the class looks like this. We have zip file, it's a C++ member, and no more resource management code, but there's still something I don't like here. This is explicit, and I mean, I'm writing Python code. Why should it say CPP member? That makes no sense. So we can do better. Python has what's called type annotations. Annotations are a wonderful thing. They do absolutely nothing. They're just objects that can be attached to different things. They can be attached to variables, they can be attached to functions, classes, return types, function arguments. Everything can have an attribute, annotation assigned to it. At runtime, it does absolutely nothing. It sometimes uses static type checking, but it is stored and it is accessible at runtime, which is the important part. Now, what we want to do now is instead of assigning the members directly, we go to our CPP class method, function and add a function to create all the members. What we do is we go through the annotations, and for every annotation we assume that this is a new member variable, and we create a new member, a CPP member. We create a CPP member object. Since the class has already been created, set name would not be called automatically, so we call it ourselves with the name of the variable we got from the annotations, and then we assign it to the class in the same name. Additionally, we save all the member names for later use. Then, in the exit method in our destructor, instead of going through all the members of the class and checking whether they are variables or not, we just go over the names, and we already know those are member variables because that's what we defined, and so we destruct them. Now, we're basically done. We have 7 lines of code, and no lines are for resource management, and everything just works very transparently. Now, you might claim that the zip file annotation is for resource management, but then I would say no, it's for readability, and you want to set the type so everyone would know what happens there, and since it's my talk, you have to agree. So what did we do so far? Everything is automatic. Destructors are called when they're needed. We don't need to do anything for that. Everything is composable. If we add a new member, it just works. We don't need to add any special code for handling that. And everything is implicit, assuming you write a specific type of code. I mean, you need to import the module, the magic from C++, and you need to make sure that you write the constructor and destructor the right way and use annotations. If you do that, everything just works with wonderful C++ destructor semantics, and you're basically good to go. We don't need to add any special code to our code. There's no change in the interfaces when we add a new destructor, and it does not pollute the interface as we go higher up. Yes, that's lying because we have to write all of the code in this method, and if you just use regular Python code, nothing would work. But assuming you write all your project this way, if you add a new destructor to your code, you don't need to make any further changes. Any questions? Okay. Before we continue to some bonus content, I want to thank a few people. Barak Itkin for helping me with this talk and going over my content again and again and again to make sure everything is okay. Adi Shavit and Balevi from the CPP conference, the core CPP, conference that encouraged me to submit the talk, and the entire NDC staff for helping with the many, many annoying questions I had before going here. And now for extras, we're going to cover 3 things. 1, return values. 2, this, and 3, member access specifiers. And this is going to be fun with live coding. Oh, can you see? Okay, can you see the code, or should I make it larger? Better? Or should it be larger? Okay, great. So the first thing we want to do, when we created a function, we created some variable inside the function, and then we returned the variable from the function, the variable got destroyed because we left the scope, we call it destructor, and that's not very useful for anything. I mean, I call a function to create an object. I want to get that object back in a working state. Otherwise, what am I going to do in my code? So we can solve that fairly easily. And this is the CPP function decorator we used before. It has a bit of extra code, but we'll ignore it for now. We call our function and we get a return value. Once we get a return value, we know that it left the function. So just like what we did before, so with member variables, we know we can remove it from the current scope. However, after we remove it, we need to assign it to a new scope. Before we assigned it into the class scope. Now we don't have a class scope, so we need to assign it to the parent scope, which is the calling function. Do it using rebind to parent destructor. we check whether the function is a CPP class function, whether the object is a CPP class object. If it is, we remove it from the current scope and push it into the parent scope. And then we can return values freely. Passing arguments, however, is a completely different subject, and we are not going to cover that. Essentially, lifetime semantics are a big and complicated subject that we're not going to delve into, because even in C++ it's complicated. Now, the next thing we want to do is this. I mean, I know that some of you are Python programmers, but some of you are C++ programmers. And coming from C++ to Python, or from basically any object-oriented language to Python, it's quite annoying that you have to write self everywhere. You have a function that takes no variables, it takes no arguments, self. You have a function that takes some arguments, self, and then everything else. It gets quite cumbersome to write it all the time, and we just don't want it there. It would be a lot nicer if we could just remove that annoying thing and just access this. So we're going to use the same tricks as we did before. Naturally, a global variable, because those are the best, called this, so it's defined everywhere and we can just use it. And then we need to somehow know what object is this object. So we add another scope. Just like we did before with the destructor scope, we create a this scope. This scope is specific to methods and not functions. So now we have a method decorator and a function decorator, which work slightly differently. When we create this scope, we take the self object and push it onto a global this stack. Again, global stacks are a wonderful, wonderful thing, and maybe not in production code. And then, because in Python, we don't have a copy assignment, we don't have assignment operators or anything like that. When we assign the new variable, a new value to a variable, we just rebind the name. Nothing else happens, no call gets called, just a pure assignment, and we bind the name. So if instead of using a proxy, we would just assign to the this variable, and nothing would work. It would just be a new variable, and nothing would actually happen. Instead, we use a this proxy. The this proxy is fairly straightforward. It uses special methods in Python. GetAttr allows us to hook into the member access in Python. If the name of an attribute is not found, we call the getAttr object. Just a sec. We call getAttr underscore getAttr to get the attribute of the object using our code. In this case, we would get to the top of the this stack, ask for the name of the attribute using getAttribute, and return the same for setting. And then you can write code that uses this everywhere and completely ignores self. Additionally, as you can see, we capture the self variable in our wrapper and we just don't forward it into the function. So now we can just write a greeter this way, and we just pass in the name, no self, use this, and everything will just work perfectly, which is really fun. Now, one thing that in my experience C++ programmers really hate about Python is access specifiers. I mean, in C++ we have public, private, protected, and it actually does something. In Python, well, it's a bit different. If you want to create a public method, we just create a method. Wonderful, everyone can access it, and we're good to go. If you want to create a private method, we just append an underscore, prepend an underscore, and then everyone knows that it's a private method and they should never, ever call that. Which means that if they accidentally need to access something internal in your class, they would definitely call that, and you would never be able to change that code ever again. So Python gives us another option, which is using a double underscore. When we're using a double underscore, every access to that function from outside the class would have to use a mangled name, which is underscore underscore, name of the class, another underscore, and then the method. That would absolutely prevent people from using it, right? I mean, you've never hacked anything weird in your code to access something internal. Even not in Python, not in C++, not in any language that you've ever used. So we might be able to do better to actually have access specifiers. Something like this maybe, where name is private and the rest is public. So what are we going to do here? This is a bit more complicated. It's going to include most of what we did so far. It also doubled the size of my library from around 180 lines to around 360. Because it's a lot simpler than the rest of the code. So first we need to create our access specifier to have public, private, and protected, as one does. Our default access specifier is, of course, private because we want to be on the safe side. And we have some global access variable to store the access. Now, when we create a function, a class, the code goes as follows. We start from the top and start defining things. Here we have a name. It doesn't have a value, only an annotation, so it goes into the annotations dict. Then we call public, we'll get to that in a moment, and we define some functions. Functions just go into the class, and we have functions. Additionally, everything that we define here is in a new scope. That's the class definition scope, which exists as long as we're defining class. We can run any code we want in here. For example, we're calling a function inside the class definition. It's called when we define the class, not when we instantiate it. So what do we actually do here? Well, obviously we set the access, which goes as follows. And whenever we call a set access, we go through all the members that already exist in the class. We use the stack to get the local variable scope and take all the variables from there and the annotations. We check which variables are new in there, and all the new ones get assigned the current access level. We save that in the access dictionary that we defined earlier with the name of the current class. So that we know those access specifiers belong to those variables inside this class. So basically when we go through the greeter, once we call public, name would be set to private because it's before the call to public, and nothing would happen to those. They would stay floating around with no access specifiers. Then in CPP class, when we create the class methods, we also get the member access for every class and pass it to the CPP method function. I think class, and method function and class function and all that gets a bit confusing. So basically check the global access dict for the current class. If none exists, we just take a default one, which would just have a private access specifier. And then for every member in the class, we get for that member name the current access specifier. If none exists, we default to private. So if we just created one function, we didn't call any access specifiers, it would be private. And since each time we call an access specifier, we change the current specifier for that class to whatever specifier it was, in this case, public. So when we create the class, those functions would be public. Any questions so far? Okay. Also, since this is live coding, stop me if I'm missing something or if you need any explanations. Then, in CPP method, we need to check the access. We know that we were called, we need to know who called us and how. So to know where we were called from, we create a caller scope. Just like the previous scopes, it's a stack, it's a global stack that stores the callers. It can either store a function caller or a class caller. If it's a class caller, we add the class itself. If it's a function caller, we just add the function. Then, when we call check access, we get the current caller so that we know who called us and check whether the current caller can access this specific function with the current access. So we basically go, if the caller is none, which means we are from a regular Python function with no CPP functions in the middle, just say, yeah, we can use that because I want to be able to write tests and I want to be able to use my code from Python code that is completely unaware of all my shenanigans. Then, if it's public, we can always access. If it's protected, we check whether the current class is an instance of the same class as before, and this also works with subclassing, so we're on the safe side. And if it's private, we make sure those classes are of the same type. If none of those things apply, we just return false. And this is what happens for methods. For variables, we have our CPP member, and we call check access on the get and the set methods. And so we get basically the same behavior, and both for functions and for variables. Now we can go to the greeter, and we know that this is public, so we can run the code, and everything works. However, if I remove the public and call it again, we get an access error because we're trying to call a function that is private. And that's basically it. Any questions? Okay, thank you. Yeah, also, if you want, the code is online, and the slides are going to be online as well. Thank you for coming.